Today we are going to design a steel beam with web stiffeners. This is George Kamiti and welcome to our today's lesson. A simply supported beam is to span 5 meters and support uniformly distributed characteristic dead and imposed loads of 200 kilonewtons per meter and 100 kilonewtons per meter respectively. The beam sits on 150 millimeters long bearings, 8 supports, and both flanges are laterally and torsionally restrained as shown in the figure 4.17. Select a suitable UB section to satisfy bending, shear, and deflection criteria. Also check web bearing and buckling at supports and design stiffeners if they are required. Figure 4.17 is showing a uniformly distributed dead and imposed loads subjected on a simply supported beam spanning 5 meters long. The dead load is 200 kilonewtons per meter and the imposed load is 100 kilonewtons per meter. So let's see how we are going to design this steel beam with web stiffeners. Thank you. Starting with the design loading. So here we are going to have design load. That is W. This will be given by 1.4 GK plus 1.6 QK. GK denotes the dead load and QK denotes the imposed load. We got a dead load of 200 kilonewtons per meter UDL and an imposed load of 100 kilonewtons per meter. Therefore, the design load will be given by GK, which is 200 kilonewtons per meter, that is the dead load, times 1.4 plus QK, which is 100 kilonewtons per meter, multiplied by 1.6. And this happens to be 200 times 1.4, that is 280. 100 times 1.6, that is 160. And when you add 280 plus 160, you get 440 kilonewtons per meter. Therefore, that is the design load. After getting the value of the design load, we are going to calculate the shear force. And in this case, if we refer this side, the left hand side as A and the right hand side as B, the reaction at A will be equal to the reaction at B, since this beam is symmetrically loaded. This is a simply supported beam. Therefore, it means that the support A and the support B are sharing the loads equally. That is what we call symmetrically loaded beam. Therefore, in this case, we are going to have RA, the reaction at A, being equal to the reaction at B, and this will be given by WL divided by 2. So this is going to be W, which is 440 kilonewtons per meter, multiplied by the span of 5 meters, and then we divide this by 2. And when we do so, we are going to have the reaction at A being equal to the reaction at B being equal to 1100 kilonewtons. And we know that the reactions are equivalent to the shear force. Therefore, the shear force will also be 1100 kilonewtons. 1100 kilonewtons. Therefore, that is the shear force. So after determining the shear force, we are going now to determine the design bending moment. And the design bending moment, that is M, will be given by WL squared divided by 8. Since the shear force at the center of this beam, can call it point C, is 0. And when shear force is 0, bending moment is maximum. Therefore, the maximum bending moment at C, that is the design bending moment, will be given by WL squared divided by 8. Remember, the beam is being loaded with uniformly distributed load. So from structures 1, that is where we get this formula. Therefore, this is going to be 440 times L, the length of this beam, the span, 5 meters, therefore 5 squared. We divide this by 8. And this is going to give us a design bending moment of 1375 kilonewtons meter. 1375 kilonewtons meter. Therefore, this is the design bending moment. So we are done with the step 1, that is calculation of the design bending moment, which we got it as 1375 kilonewtons meter, as well as the calculation of the shear force, which is 1100 kilonewtons. From there, we are going to step number 2. And in this case, step number 2 is the initial section selection. Therefore, we go to initial section selection. Initial section selection. And when we are selecting the section, we need to know the minimum plastic modulus about the x axis. Therefore, the minimum plastic modulus should be greater than the design bending moment divided by the design strength of steel, that is Py, and in this case we are dealing with the S275, meaning that the design strength of this steel is 275 newtons per square millimeter. Therefore, the plastic modulus will be given by the design bending moment, which is 1375 kilonewton meter. We need to convert that to Newton millimeter. Therefore, we multiply 1375 by 1 million. So this is going to be 1375 times 10 raised to the power of 6 divided by the design strength of steel, 275 newtons per square millimeter. And this is going to give us 5,000 times 10 raised to the power of 3 cubic millimeters. Therefore, the plastic modulus should be greater than 5,000 times 10 raised to the power of 3 cubic millimeters. We learned that from Appendix B the plastic modulus is usually given in cubic centimeters. Therefore, you need to convert cubic millimeters to cubic centimeters. And this means now that the plastic modulus will be greater than 5,000 cubic centimeters. Since 1 cubic centimeter is equivalent to 1,000 cubic millimeters. And therefore, the serial sizes of the sections you are going to choose must have a plastic modulus greater than 5,000 cubic centimeters. And choosing now the sections from Appendix B, we are going to try the following sections and compare and contrast and select the more suitable one among the ones that we are going to select. And the first section that we can select, we have a serial size of 610 by 305 by 179 universal beam section with a plastic modulus of 5,520 cubic centimeters and the steel strength of 265 newtons per square millimeters, and this happens to be classified plastic. The second section will have a serial size of 686 by 254 by 170 UB section, that is universal beam section, having a plastic modulus of 5,620 cubic centimeters. The strength of the steel section being 265, classified in class 1 plastic. Let's try another section, section 3, with a serial size of 762 by 267 by 173 universal beam section. This one have got a plastic modulus of 6,200 cubic centimeters with steel strength of 265 newtons per square millimeters, being classified in class 1 plastic. Having the 3 sections, the most suitable section appears to be section number 2, since it has the least depth of 254 among the 3, and it has, or we can say that it is the lightest among the 3, since it has a mass of 170 kilograms per meter. Therefore, section 2 appears to be the most suitable section. Therefore, this is the section we are going to work with and see whether it is satisfactory in different criteria or categories. Then, after selecting a suitable section and classifying the section, the step number 4, since step number 3 is classifying the section, therefore we can say that we are also done with step number 3, which happens to be classifying the selected sections. The step number 4 is a calculation of shear strength. Therefore, I go to shear strength calculation. Shear strength. And in shear strength, we need first of all to calculate what we call the shear capacity of the section that we have selected. Therefore, shear capacity, that is PV, is usually given by 0.6 PYTB, whereby PV is the shear capacity of the section, PY is the design strength of steel, T is the thickness of the web, and D is the depth of the section. Therefore, the shear capacity of the section will be given by 0.6 times the strength of this steel section is 265 newtons per square millimeters. Therefore, we multiply that by 265 times the web thickness from appendix B of this section is 14.5 millimeters, and the depth of the section from the same appendix B happens to be 692.9 millimeters. And when we do so, we are going to have a shear capacity of 1597 times 10 raised to the power of 3 newtons. Converting this to kilonewtons, this is going to give us, we're going to divide this by 1000, since 1 kilonewton is equivalent to 1000 newtons. Therefore, 1597 times 10 raised to the power of 3 newtons, that happens to be 1597 kilonewtons. So that is the shear capacity. And we know with comparison, the shear force, that is FV, should be less than the shear capacity, that is PV. And therefore, we find that the shear force, which is 1100 kilonewtons, is actually less than 1597 kilonewtons, which is the shear capacity, and therefore it means that the section we have selected is okay when it comes to resisting excessive shear. But we also need to know whether we are dealing with high shear load or low shear load. And we know that if FV is greater than 0.6 PV, then it means that we are dealing with high shear load. 0.6 PV happens to be 0.6 times PV, we have it as 1597 kilonewtons, and this is giving us 958 kilonewtons. Therefore, you find that FV, which is 1100 kilonewtons, is actually greater than 0.6 PV, which is 958 kilonewtons. And this means that this is a high shear load. That is a high shear load. All right. So we are done with the step number 4, that is a determination of the shear strength, and that's what we got. From there, I go to step number 5, and step number 5 is determination of the bending moment capacity. Therefore, you go to bending moment, or what we call moment capacity. And we know that the moment capacity is given by the design strength of steel times the plastic modulus of the selected section. And in this case, the design strength of Steel, especially the section we are dealing with, is 265 newtons per square millimeters multiplied by the plastic modulus of this section, section 2 that we are working with, of 5620 cubic centimeters. We need to convert that to cubic millimeters. That is, we multiply this by 1,000. Therefore, 265 times 5620. Then we multiply that by 1,000 to convert it to cubic millimeters. And therefore, the moment capacity of this section happens to be 1,489.3 times 10 raised to the power of 6 Newton millimeter. We need to convert this to kilonewtons meter. Therefore, we are going to divide it by a million, since 1 kilonewton meter is equivalent to a million Newton millimeters. When we do so, we are going to have a moment capacity of 1,489.3 kilonewton meter. Therefore, that is the moment capacity of this section. We know that for class 1 plastic, for class 1 plastic, the moment capacity should not exceed 1.2 PYZ. Therefore, moment capacity for class 1 plastic should be less than or equal to 1.2 PYZ. And we know that Py is the design strength of steel and Z is the elastic modulus of this section obtained from Appendix B. And therefore, the moment capacity will be less than or equal to 1.2 times the design strength of this steel, 265 newtons per square millimeters. Therefore, multiply that by 265 times, from Appendix B, the elastic modulus of this section is 4910 cubic centimeters. We need to convert that to cubic millimeters. Therefore, we multiply 4910 by 1,000. Therefore, 10 raised to the power of 3. And this happens to be 1,561.3 times 10 raised to the power of 6 Newton millimeters. When we convert that to kilonewton meter, we find that MC should be less than or equal to 1,561.3 kilonewton meter. Therefore, MC, which in this case we have, or we got it as 1489.3 kilonewtons, we find that it is actually less than 1561.3 kilonewtons, meaning that that section is okay. Therefore, you can say that since MC is less than 1.2 PYZ, then the section is okay. But all in all, we also need to calculate the total moment. And the total moment is usually given by the design moment plus moment due to self-weight of the beam. You already have the design moment, which is 1375 kilonewtons meter. We need to calculate the moment due to self-weight of the beam. And in this case, the moment due to self-weight of the beam will be given by WL squared divided by 8. And in this case, W will be given by the mass of this section is 170 kilograms per meter, which in other words we call mass per meter. And therefore, we need to convert 170, we need to convert it to newtons, in kilonewtons per meter. Therefore, 170 kilograms per meter. For us to convert mass to weight, we need to multiply the mass by the gravitational force, which is 9.81 newtons per kg. Then to convert newtons to kilonewtons, we divide by 1,000. That is 10 raised to the power of 3. Therefore, this is W. Then we know that the design load is usually given by 1.4 GK. Therefore, this is GK, the dead load. And this dead load is what we are calling the self weight of the beam. So we are going to multiply this dead load, which is 170 times 9.81 divided by 1,000. We multiply it by 1.4, and then we multiply by the square of the span of this beam, which is 5, and then we divide by 8. Therefore, the moment due to self-weight of the beam will now be given by 1.4 multiplied by 170 times 9.81. Then we divide this by 1,000. Then we multiply that by the square of the span of this beam, which is 5 squared, and then we divide that by 8. And by doing so, we are going to have the moment due to self-weight of this beam as 7.3 kilonewton meter. 7.3 kilonewton meter. Therefore, the total moment will be given by the design bending moment, which in this case we got it as 1375 kilonewton meter. 1375, we add the extra moment due to self-weight of the beam, which is 7.3 kilonewton meter. And when we add the two, we are going to have 1,382.3 kilonewton meter. Therefore, that is the total moment. And the total moment of the beam should be less than the moment capacity of the beam. Since total moment is 1382, we find that 1382.3 kilonewton meter is actually less than the moment capacity of this beam, which is 1489. It is less than 1489.3 kilonewton meter. Therefore, it means that the section we have selected is very much satisfactory, and it is able to resist any failure due to excessive moment. So we are done with step number 5, bending moment capacity. Then we go to step number 6, BI. And step number 6 is determination of deflection, so that we see whether the section we have selected is able to stand and resist any failure due to deflecting. And deflection at the center will be given by this formula, 5WL raised to the power of 4 divided by 384 EI. Remember, when we have a simply supported beam being subjected or carrying a uniformly distributed load, the deflection, maximum deflection at the center is given by this formula, whereby W is the imposed load subjected on that particular beam, L is the span, E is the elastic modulus of steel, and I is the second moment of area of the selected section that is obtained from Appendix B. Therefore, the deflection at the center will be given by 5 times the imposed load on this beam is 100 kilonewtons per meter, and the span of this beam is 5 meters. Therefore, 5 raised to the power of 4. We divide this by 384 times. The elastic modulus of steel is usually given by 205. So we multiply that by 10 raised to the power of 6. Then we multiply by the moment of inertia, or the second moment of area of this section obtained from Appendix B, which happens to be 170,000 centimeters raised to the power of 4. So we need to convert that to millimeters raised to the power of 4. And we are going to multiply 170 times 10, 170,000. We divide it by 10 raised to the power of 8. Therefore, this will be 10 raised to the power of -8. And that is going to give us a diffraction at the center of 0.0023 meters. When you convert that to millimeters, we are going to have a diffraction of 2.3 millimeters. Therefore, that is the deflection of this beam at the center. We need to compare this deflection and see whether it is exceeding the maximum required deflection. And the maximum required deflection for a beam carrying plaster is given by, therefore, maximum deflection for a beam carrying plaster is usually given by span divided by 360. And in this case, the span of this beam is 5 meters. We convert that to millimeters, which will be 5,000 millimeters. And then we divide this by 360. And this is going to give us a maximum deflection of 13.88 millimeters. Therefore, we find that the deflection at the center, which is 2.3 millimeters, is less than the maximum deflection, which is 13.88 millimeters, and therefore our section is very much okay. The section you have selected is very much okay. Thank you so much for watching our video. Please don't forget to subscribe.